Okay, good morning. Let me begin by thanking Noel Clark and Don Smalley for inviting me to this very interesting workshop. Let me also wish them a happy 30th anniversary on their very important work on colloidal photonic crystals. My talk today will focus on a specific type of photonic crystal, namely those that have a three-dimensional or complete photonic bandgap. These are materials that enable the trapping and controlling of light on a very microscopic scale. Some of the properties under control include refraction, diffraction, control of spontaneous emission, as well as the guiding of light on an optical microchip, much like you have the guiding of current on an electronic chip. Structurally, these materials consist of a solid backbone, which consists of roughly between 25 to 40% by volume fraction, and therefore there's an opportunity to infiltrate other types of materials which have adaptable properties, for example, liquid crystals or nonlinear materials, and this gives these photonic bandgap materials a great deal of reconfigurability. So in my talk I will describe some of these interesting properties and talk about some of the applications as well as some of the challenges in actually micro-fabricating these three-dimensional bandgap materials. As I mentioned, one of the most striking properties is their ability to trap or localize light, and this has quite a long and rich history going back to the field of electronics, where, for example, Anderson showed that if you have a band of electrons in a solid and you introduce disorder, the band, this is the density of electronic states versus the energy, localized states begin to appear at the edges of the band, and as you introduce more and more random scattering into the system, eventually the entire electronic band can be engulfed into localized states, and therefore one might have a metal to insulator transition. This is referred to as the Anderson transition. So in this case, all of the electronic states can become localized. I got interested in this and to ask whether similar things could happen with classical waves. For example, with vibrational modes or phonons in a solid. And here there are some similarities and differences. One of the main differences is that in the very long wavelength limit, one has the phenomenon of Rayleigh scattering. That's very weak scattering. So no matter how much random scattering you put into the system, the long wavelength modes remain extended. However, there is an upper frequency cutoff, say the divide frequency of the vibrational modes, and here disorder can lead to localized modes of vibration. And so here one can localize some, but certainly not all of the states. In the case of electromagnetic waves, there's perhaps a more subtle or profound question, and that is whether one could really localize any of the states in a fully three-dimensional sense. Because here you have again the phenomenon of Rayleigh scattering at very long wavelengths, but there is no natural upper frequency cutoff as you have in the case of phonons. So if one creates the appropriate type of microstructure and scattering, then perhaps one can create an intermediate frequency window in which localized modes of light might appear. And just to illustrate the subtlety of this question, what I've done here is to construct an analogy between the Maxwell equations that govern the propagation of light with the equation for electrons and the scattering potential of Schrödinger's equation. So here, consider a dielectric medium which has an average dielectric constant epsilon 0 and a part which fluctuates from point to point in space. And then, if I construct the analogy, the electric field vector is like the field amplitude in Schrödinger's equation. The first two terms are analogous to a kinetic energy term, and the fluctuating part of the dielectric plays the role of a scattering potential. And here, the average part of the dielectric times the square of the frequency is the analog of an energy eigenvalue in Schrödinger's equation. Now, if we're dealing with materials that don't simply absorb or dissipate the energy in the system, that is the condition that one has a real positive dielectric constant, which means that the average part is larger than the maximum negative excursion of the fluctuating part. And as a result, the energy eigenvalue in that situation is always higher than the highest of these potential barriers. So unlike in electronics, where one can have negative energy states, and an electron simply being trapped between classical turning points, the question of whether one can localize light is the question of whether there can be bound states of energies higher than the highest potential barriers. And so this is just not the same as classical trapping, but really a more subtle interference effect that is required here. And creating a photonic band gap, in fact, enables this by reducing the number of pathways of light in this upper frequency regime. What you're seeing in this movie clip is actually a finite difference time domain simulation of an actual localized state in a dielectric structure which consists of a three-dimensional photonic crystal of high dielectric constant rods with a single rod missing in the middle, and I've removed the 3D photonic crystal structure above and below so that you can visualize the field. Here the red and the green arrows represent the electric and magnetic field vectors, and the shading corresponds to the energy density of the field. And there are some differences here between just a standard optical microcavity resonator and this localized state. For example, here the majority of the light intensity is focused in the region where the dielectric rod has been removed. So it's in the low index regime rather than in a traditional cavity resonator where one traps light by total internal reflection inside the high index medium. Here also, one can confine light on a very small scale, sub-wavelength scale, so that one can have both a very high quality factors, if you like, as well as a very small mode volume. And this leads to very interesting strong coupling effects between light and matter, or interesting quantum optical effects. So here's an example of a three-dimensional photonic bandgap material that we synthesized about 8 years ago at the University of Toronto in collaboration with our chemistry group as well as a group in Spain. This is something that's referred to as a silicon inverse opal structure. It was made by starting from a template which consists of a silica or glass sphere-based template sedimented into a face-centered cubic lattice, and that template was then infiltrated by chemical vapor deposition with silicon. And then finally the original template was removed by hydrofluoridic acid etching. And so what you see here are the regions where the silicon was infiltrated, these hollow shells of silicon, and the silica which has been removed from inside, as well as some holes that connect the different shells, where the actual opal spheres were sintered or touching and formed necks. This structure has a face-centered cubic lattice structure. The diameter of the spheres here was chosen to be 870 nanometers, so that the resulting structure would have a complete photonic bandgap centered at a wavelength of choice for telecommunications, namely 1.5 microns. So this is the 111 phase and the 110 phase of the electron micrographs. And on the left-hand side you see a computer-generated picture of the same. And as I mentioned, by volume, this is only 25% silicon, and the rest is just air. So one can infiltrate other types of materials into such a structure. Here I show the electromagnetic mode structure of the silicon inverse opal, starting first of all with a structure that does not have the right volume fraction of silicon to create the complete photonic bandgap. So we can look at the mode structure within the face-centered cubic Brillouin zone, this crystal looking at the irreducible part of that zone by symmetry, and then looking at the electromagnetic modes along a particular direction, say from gamma to L, and what you see in blue are the electromagnetic modes dispersion relations along those directions, and the red regions are actually gaps in the spectrum along that direction. And what I'll do is, as I sweep over different directions in this irreducible zone, the red regions will keep track of the intersections of the stop gaps. So if I continue this over many different directions, eventually you see that there's no intersection of the stop gaps in different directions. Or in other words, there's no complete three-dimensional photonic bandgap. There are just bandgaps in particular directions. So this is the overall band structure. So there's no complete gap that spans all directions in space. If I go to a structure which has a more optimal volume fraction of silicon, in this case about 25%, you see a slightly different picture that emerges when I sweep through the different directions in the wave vector space. Here, the lower stopgap disappears as I span over different directions, but there's an upper region here in which there's a complete band gap, an intersection of the stopgaps in all the different directions, and that is the complete photonic band gap, which you see here, which in this case was chosen to be centered at 1.5 microns and spans about 5% relative to the center frequency. So this is how the band structure actually emerges, and the requirement on the refractive index, which is about 3.5, and the volume fraction for creating this gap in all directions. As I mentioned, only about 75% of the volume is empty space, so one can infiltrate other types of materials, and this is just one illustration of the types of adaptability that one can build into these structures, for example, by infiltrating a pneumatic liquid crystal. So this picture is again showing the backbone made out of silicon and depicting, say, a coating of a pneumatic liquid crystal that would fill all of the interior void regions in the structure. And let's suppose, for instance, that one applies a field or somehow manages to align the pneumatic in, say, the vertical direction, the Z direction. By infiltrating this additional material, that reduces the refractive index contrast between the silicon backbone and the interior regions. So as a result of that, the photonic band gap, as I was showing before, disappears. So what you're looking at here is the total electromagnetic density of states as a function of frequency. The lower stopgap leads to a reduction in the density of states. And this region was where I showed the complete photonic band gap appearing for the case of a purely silicon-based structure. By infiltrating a volume fraction of about 37% of this particular liquid crystal, EDHA, the complete photonic band gap actually closes. The density of states really does not completely vanish at any point, although it looks like that in the picture. And this particular liquid crystal had these dielectric components in the X, Y, and Z direction. However, if one can reorient the pneumatic director field, one might change the band structure properties and basically leverage the usual tunability associated with liquid crystals with the sensitivity of the photonic band structure to those changes in the refractive index. So here you see, again, the same picture in which I blow up the region where I had a photonic band gap in the pure silicon structure, and I consider different orientations of the liquid crystal, starting from in the vertical direction, theta equals 0. That corresponds to this blue curve in which there is no complete vanishing of the total electromagnetic density of states. But if I rotate that liquid crystal to these different angles relative to the vertical, you can see that the complete photonic band gap can be reopened. So by reorienting the infiltrated material, one can either open or close the photonic band gap. And in this case, the size of the band gap that is created by reorienting the molecules by this angle 5/16 is roughly about 2% of the center frequency. So in terms of nanometers at 1.5 microns, this would be a 30 nanometer bandwidth photonic band gap that can be opened or closed simply by reorienting the material inside. So this gives you an idea of the magnitude of these types of reconfiguration abilities of the photonic band gap. If one was doing temperature tuning, going from, say, a pneumatic to an isotropic phase, one could have about a 5% tuning, or about 75 nanometers of either opening or closing the band gap. So these are some of the properties that you can keep in mind as I go through some of the more standard properties of photonic band gap material. Am I giving you one?
Can we just find some more help for this?
Maybe the previous.
Maybe it was next door. Okay, so thanks. Sorry to interrupt.
Okay. Thanks. Okay, let me This is a slightly different way of looking at the electromagnetic band structure associated with a phase-space portrait. So what you're looking at here is a picture in K-space, and these very colorful pictures that you're showing, as you're seeing, are called isofrequency surfaces as a function of frequency. So let me just go back to the beginning of the movie clip here. So each point on the surface corresponds to a different electromagnetic mode for this dimensionless frequency. So if I go to very low frequencies, or wavelengths very long compared to the scale of the lattice constant of the structure, it's a spherical shape. All different directions in space are equally well available. So I'll come back up in frequency. We'll see the spherical shape enlarging. The total surface area here is the total electromagnetic density of states at that particular frequency. So as the frequency now becomes larger and the wavelength becomes comparable to the lattice constant, you see these stop gaps opening up in different directions where electromagnetic propagation is forbidden in those specific directions. But nevertheless, there are modes in other directions. So these different colors correspond to different bands. Eventually, you will reach a frequency regime where the entire isofrequency space disappears. That corresponds to the existence of this complete photonic band gap, the non-existence of states in any direction in space. And so another point of this picture is that the conventional criterion for localization suggested by Yaffe and Raven back in the 1960s was that when the mean-free path for scattering of light becomes comparable to the wavelength divided by 2 pi, then one might expect localization to take place. In this case, we have a more general criterion, which is stated here, that it's the product of this phase space, the surface area that you're seeing here, times the square of the mean-free path. When that is of order 4 pi, then one can realize localization. If the phase space is simply spherical, that reduces to the traditional Yaffe-Raven condition. But as you see here, the phase space can be made much smaller than 4 pi k squared, the surface area of the sphere. One can very easily trap the localized light by introducing some additional scattering. The shapes of these isofrequency surfaces also have a very important role. They determine the nature of refraction of light as it enters and leaves the structure. Refraction, or Snell's law, can be regarded as basically describing the conservation of energy as well as the momentum of the light parallel to the interface. And one can regard that in both the k-space picture as well as in coordinate space. So if I look at it in k-space, suppose that I'm having light entering the medium whose refractive index is 2 from, say, air. The isofrequency surface in air is shown here. The refractive index is 1. But here, with the refractive index of 2, the radius of this isofrequency surface is larger than that of air. And the conservation of the energy and momentum simply means that this basically describes Snell's law of refraction. You consider the incident wave vector, which is described by a green arrow that you'll see, which lies on the isosurface of air. One constructs the wave vector parallel to the interface and requires that be conserved, and that the final refracted wave vector lie on the isofrequency surface of the medium. And finally, the direction in which light propagates in the medium is in the direction of the group velocity, which is in the direction normal to the tangential surface of the isofrequency surface. So here, if one can change the isofrequency surfaces themselves, one can change the law of refraction completely. And one gets a variety of different effects, such as negative refraction, where the light can actually bend backward rather than in the forward direction. One can have refraction which is out of the plane of refraction completely, as well as other interesting effects such as superprisming, very small changes in the incident angle. One can have very large changes in the refractive beam, etc. So that's all controlled, again, by the microstructure of the photonic crystal and the shape of these isofrequency surfaces. So here you see an example of a photonic crystal which has, instead of the face-centered cubic symmetry, a cubic symmetry. This is a photonic crystal which is basically etched pores in the silicon background. This is a structure that was actually made in Germany. And these pores are modulated, and so this creates a cubic lattice symmetry. This is the band structure associated with that. And as I sweep up the band structure, you can see the shape of the isofrequency surfaces changing from spherical eventually to shapes that have a cubic type of structure, which reflect the cubic symmetry of the crystal itself. And this cubic isofrequency surface gives rise to some very interesting types of refractive behavior as light enters and leaves the structure. So here I'll just focus in on one particular isofrequency surface which has this cubic structure. Let me just stop that there. And what I'll consider is the incident and refracted beam determined using that construction that I showed on the previous slide. So blue is the direction of the incident light, and the red arrow defines the direction of the refracted beam. And so what happens here is that as light enters the medium over a broad range of incident angles, it's refracted at a very acute angle, nearly parallel to the interface. And what that means is that light can be very efficiently trapped in a very thin film. So here you see the refracted beam. It remains in a specific direction for a broad range of incident angles. And as one goes through different directions, it changes slightly. But the basic idea is if you have a thin film, light from the sun is coming in, for instance, the light is being refracted largely parallel to the interface, and it has a very long dwell time in the structure. So as we heard in the previous talk, one of the aims of photovoltaics is not only to just efficiently harvest electron hole pairs that are created, but to trap photons efficiently so that a large fraction of the entering photons are converted into electron hole pairs. And this is a mechanism for trapping light very efficiently. So here you see a depiction of a thin film of this type of photonic crystal and the band structure associated with it. And where the curves bend over, these are modes in which the group velocity vanishes. So here, for instance, the light you can think of as bouncing back and forth many times before escaping. And so if one introduces a small amount of absorption into the material, say that corresponding to silicon, and for visible light, which would be an absorption length, which would be about 50 times the lattice constant here, what you see are various absorption peaks at different frequencies corresponding to the band structure. Down here, there's a small fabric-pearl resonance of the overall film, which you can barely see. This peak here corresponds to the slow group velocity mode, the longitudinal slow group velocity mode that you see. And here, in these bands, you get this parallel to interface refraction effect, which I described on the previous slide, where light entering over a broad range of angles from this side gets deflected into a slow group velocity mode that bounces back and forth in this direction before it's either transmitted or reflected. And here you can see absorption peaks corresponding to different directions of incidence, in which on the order of 50% of the light can actually be absorbed within a thin film structure like this. So we think this is a very promising way of engineering refraction and trapping of light to actually harvest a large number of photons in a thin film microstructure. The synthesis of three-dimensional photonic band gap materials has also been a tremendous challenge over the past couple of decades, actually. And one of the more recent approaches is using optical lithography to create these materials. Here you see a structure that is made by what's called direct laser writing. So one focuses a laser beam onto a small voxel, as it's called, in polymer photoresist, in this case it's SU8. That causes photopolymerization or cross-linking of the polymer in those regions where the exposure intensity and duration exceeds a certain threshold. And then one can move the laser pen as one wishes to create an arbitrary structure of exposure, and then under development the unexposed regions are dissolved away, leaving behind this three-dimensional photonic crystal in this photoresist structure. The refractive index here is only 1.67, so that is not sufficiently strong scattering to create complete photonic band gap. And so what we've demonstrated recently in collaboration with the group in Karlsruhe, Germany, of Martin Wegner, is a way to extend the inversion technique that I showed for the inverse opal structure. This is a double inversion technique. So what is done is one direct laser writes and develops the structure in the SU8. Then one does room temperature chemical vapor deposition of silicon dioxide into the structure. And then removing the removing the SU8 creates an inverse replica of the direct laser written structure in now glass. And now the glass inverse template can withstand the high temperatures required for chemical vapor deposition of silicon. So then we repeat the same steps that we did for the inverse opal structure. And here you see a direct replica of the laser written structure now made out of pure polycrystalline silicon. And that was after hydrofluoric acid etching of the SiO2. So what this shows is that any structure that can be created by optical lithography like this can in principle be replicated with a high index semiconductor such as silicon using this double inversion technique. Now direct laser writing is a serial process. You have to do one voxel at a time, and so if you want to make a very large structure, then it becomes both time consuming and difficult because alignment issues become critical as the structure becomes larger and larger. So one would also like to have a more parallel approach for creating a large-scale photonic crystal. And so a lot of interest has been focused on doing this by multiple beam interference. So consider having 4 laser beams exposing a photoresist. This consists of beams with specific directions, phases, polarizations, and amplitudes. And the intensity pattern is given by the square or the sum of these individual amplitudes. And the question is, when the intensity exceeds a certain threshold, then one gets the photopolarization taking place again. And the question is there a choice of these beam parameters such that one can create the right architecture leading to a complete three-dimensional photonic band gap? And as it turns out, there is a way of doing that, choosing the right types of polarizations and amplitudes of the beams and then aligning them all correctly. This also is a somewhat difficult thing to do in terms of alignment and so on. So what we were interested in was there a way of simplifying this to do it with just a single laser beam which illuminates a type of diffraction gradient or optical phase mask that would create the same type of interference pattern that could be generated by multiple beam interference. And so here you see a depiction of this structure, or what we call an optical phase mask, which does that. This phase mask consists of 2 orthogonal gradients, you see above and below, separated by a solid layer in between. The gradients, as you can easily see, create diffraction in both the x and the y direction. This creates the x, and the one below causes diffraction in the y direction. And one can choose the material parameters so that only the leading order diffractive beams actually propagate downward into the photoresist, and the higher order diffractive beams are forced to be evanescent. Finally, this middle layer here is important for selecting the relative phases of these 5 beams, the central beam and the 2 diffractive beams of the x and y direction, such that the resulting 5-beam interference pattern gives rise to the right photonic direction. So here you see a more detailed depiction of that. So 5 beams are coming down into the photoresist, starting from a single beam at the top, which is linearly polarized 45 degrees with respect to the gradients. And so the idea here is to encode all of the architecture of the photonic crystal geometry into this optical phase plate. And so here you see some typical iso-intensity surfaces that are created in the photoresist below the mask, going from low to high intensity, where the color turns to about brown is the ideal architecture for creating this three-dimensional photonic band gap structure. And again, the intervening layer is very important, selecting the relative phases. Here you see a volume cut through the intensity pattern. So red is high intensity, blue is low intensity. So the exposure pattern will follow what you see in red here. These are basically zigzag patterns of high intensity in the X and Y direction stacked on top of each other. And this is basically the architecture of a diamond lattice, which is what one needs to create a very large three-dimensional photonic band gap. So if one now takes this exposed and developed photoresist and replicates it with silicon, one would find a photonic band structure diagram that looks like this, in which there's a very large three-dimensional photonic band gap, which now spans 24% relative to the center frequency. And we studied the properties of these types of phase masks, varying the depth of these grooves, the width of these ridges, and the thickness of the intervening layer. And this is just a picture of the space of parameters W, D, and T, such that if you work with a phase mask with these parameters contained in this blue region, that would again lead to a complete photonic band gap with a band gap of at least 20%. So these phase masks are actually very robust and a very efficient way of creating band gaps on a very large scale. So that describes how one would create three-dimensional band gap materials. One would also like to create circuits for light inside of a three-dimensional structure like that. Now, in the past, a lot of attention has focused on what was considered easier to micro-fabricate, namely these types of two-dimensional photonic crystals. So here you see a particular type of device. A waveguide is created here by removing or not creating a row of holes in this membrane-type structure, which has a finite thickness in the vertical direction. And so many frequencies of light could be guided through the otherwise forbidden band gap through this waveguide channel. And beside that, you see some holes which have slightly different diameter than the background holes. And these act as resonators that pick up particular frequencies and which can guide them in different directions. So this is used for demultiplexing a signal in which many different frequency channels are propagated, and specific ones can be guided in other directions. Here, the confinement of light is by the band gap effect of the vertical in the transverse direction, but by total internal reflection in the vertical direction. One of the problems with total internal refraction is that if you have some disorder in the system, say that these holes are not made perfectly, then one can very easily have escape or scattering of light into the third dimension. So the total internal reflection mechanism is not very robust in the guiding of light. So here is an FDTD simulation showing what happens if you put in a random diameter variation of 25 nanometers into all these holes. You can see that the light escapes into the third dimension very easily over a relatively short length scale. And so this is one of the reasons that we consider looking at three-dimensional band gap materials for complete confinement of the light. So here you see what we call a 2D, 3D heterostructure. So this is a three-dimensional band gap material which sandwiches a two-dimensional microchip layer and the corresponding band structure associated with that. So the white region in the middle is the overall three-dimensional photonic band gap of the cladding region, and introducing this planar defect in this otherwise three-dimensional periodic structure creates some modes here, waveguide modes inside the gap, in which light can propagate in the plane of this microchip but can't escape into the vertical direction. And one can choose the parameters here, the diameter and the height of these rods, such that one can confine these planar guided modes to a certain fraction of the overall three-dimensional band gap, leaving behind this cross-hatch region, which I refer to as the on-chip three-dimensional band gap. So this continues to be a complete 3D gap in this region. And then one can remove a line of rods in the planar microchip layer to create a waveguide channel which spans this on-chip three-dimensional band gap. So these are the two-dimensional guiding modes. These are 3D modes, and this is the overall 3D band gap. Now, by removing the row of rods, one creates a waveguide channel in the on-chip photonic band gap. And one can play with the parameters, the height of these rods in the 2D layer, the radius of the rod, and find out what is the maximum waveguiding bandwidth that you can create with these single-mode waveguide channels. And as it turns out, it's about close to 200 nanometers of single-mode waveguiding created in these waveguide channels. And so here you see a picture of a 2D, 3D heterostructure that was created by direct laser writing, and again in the group of Martin Wegner in Karlsruhe University, where you see, this is just a computer-generated picture, these are the actual SEMs. Here you see rows of dielectric rods that have been left out, which act as the templates for waveguide channels. Above and below, there's 3D photonic crystal material, which sandwiches this microchip layer. So what this suggests is the possibility of guiding light in a three-dimensional path within the appropriate architecture. And so this just depicts the idea that one could have many of these two-dimensional microchip layers stacked on top of each other, separated by three-dimensional photonic bandgap material. This is the outline of a vertical waveguide link. So if one removes material from the 3D cladding layer, where you see these blue boxes, that will create a vertical waveguide link from one microchip layer to the next. And in a moment you'll see a finite difference time limiting simulation of light being guided along this circuit path. So this allows light to flow through these sub-wavelength apertures without diffractive losses taking place. And the bandwidth over which that can be done is about 200 nanometers, meaning that hundreds of different wavelength channels of information can flow through this circuit path, unlike in electronics where you have a single channel of information flowing through the 2D chip. So here you have 3 dimensions of geometrical integration, as well as an additional dimension of wavelength bandwidth. So I refer to this as 3 plus 1 dimensional integrated optics. So these waveguide channels consist of air, so light is propagating primarily through air, and there's no problem, as you have in electronics, of heat dissipation, etc. So this might be a very interesting way of guiding light on a chip, and now we have at least the design rules for creating these three-dimensional circuit paths. So this is a more detailed finite difference time domain simulation showing the flow of light. This is the red arrows describe the electric field vectors, and green arrows in the moment you'll see are the magnetic field vectors. This is a simulation of light at a wavelength of 1.5 microns propagating through this waveguide channel. The separation between the rods here, center to center distance, is 600 nanometers. And up here you see the results of the light transmission characteristics as it goes around this three-dimensional circuit path, showing that if one chooses the architecture appropriately, as I've shown in this picture, one can get very high transmission over a bandwidth which ranges typically from 100 to 200 nanometers. The light has no way of escaping in any other direction because of the bandgap material that surrounds it. It can only go forward or backwards. And the amount of backscattering that takes place can be kept to a minimum through the appropriate choice of microstructure. The blue arrows just depict the pointing vector showing the flow of light along this circuit path. The speed of light on the on-chip or planar microchip layers is about a third of the speed of light in an ordinary vacuum, and through these vertical layers, 1/8 the speed of light in an ordinary vacuum. Just one? Yeah. Okay. this demonstrates that at least the design rules are there. Now it's really a micro-fabrication challenge to make these structures accurately and to actually observe the guiding of light within these types of microchips. But Maxwell's equations do allow for this type of high bandwidth guiding of light in a three-dimensional type of architecture. Okay, another thing that is of interest is to couple light from a fiber to this type of microchip. And here there are some issues. One is the fact that if you take a traditional conventional fiber, the core is on the order of 10 microns, whereas the waveguide channel here is less than a micron in cross-section. And so as a result of the mode mismatch, size mismatch, as well as a change in geometry from the fiber to the chip, a lot of light will be lost at the interface between a fiber and this chip. So one of the things that we've looked at is how to change the structure of the fiber, perhaps through these photonic crystal type of fibers, as they're called, in which you can create a two-dimensional microstructure that goes along the axis of the fiber itself and guide light through a small mode core area to couple light efficiently from fiber to chip. So what I'll just show you is a two-dimensional version of this fiber to chip coupling, in which this 2D, 3D heterostructure is just modeled by a two-dimensional photonic crystal with an air waveguide. And I can model these microstructured fibers, say with a solid core, small mode volume, mode area of the solid core, by just the central slab region, which is just a solid SiO2 core like this. Here you see what happens if you take light coming from the waveguide inside the photonic crystal and allow it to enter free space. There's a very broad diffraction pattern because this is a sub-wavelength aperture. And this is looking at different wavelengths as you see the different snapshots here. So there's a lot of diffractive loss in unwanted directions. And not only that, there's an impedance mismatch between the photonic crystal and the air outside. Here you're seeing the reflection. There's about a 10% back reflection into the waveguide itself as it enters air. So what we've done is to change the structure of this waveguide exit port to modify this diffraction pattern. And the way we've done that is to remove two of the adjacent rods on either side of the waveguide and add slightly larger rods, the next nearest neighbor. These act as resonators, which can be excited by the light coming through this waveguide, and the resulting pattern of light outside is a combination of the beam coming directly from the waveguide as well as the scattered light from these resonators. The resonance associated with these larger rods is this frequency here, and you might recall from, say, a course in quantum mechanics that if you have the light incident on the resonator below the resonance, then they act in phase. The scattered light is in phase with the incident light. And so what you see that below this resonance frequency, the diffraction pattern actually becomes even worse than it was before. You see the broader diffraction here. There's constructive interference of these into unwanted direction. Whereas above the resonance, there's a 180-degree phase shift, and you can get disruptive interference between the incident and the scattered field in these other directions. So that collimates the beam over several wavelengths before eventually diffraction again takes place. So one can combine that with this solid core fiber, and actually we taper the fiber a little bit to prevent the back reflection as well. And we were able to show that over a bandwidth of about 130 nanometers, one can get over 98% coupling of light from the chip to the fiber, and likewise from the fiber back to the chip, eliminating the diffraction as well as the back reflection. Okay, so finally let me talk about one last aspect. We've talked about simply passive guiding of light. Another question is, can one have some sort of active circuit element inside this waveguide circuit. For example, for controlling microlight, optical switching, or perhaps even optical transistor type of action. Now, the ideas of optical transistor action go back more than 30 years. People like IME considered a very simple architecture in which one had basically a Fabry-Perot type of cavity where inside there was a nonlinear material. So one can change the refractive index inside the medium by pumping that with another laser field, say it comes from the side, and by changing the optical path length of this signal beam, one can cause it to go from transmission to reflection as one changes the intensity of the side pumping beam. And one of the reasons that this didn't turn into a practical type of transistor device is for a very fundamental reason that if you want this to work for very low, for reasonably low intensities of the side pumping beam, one would like to engineer a very sharp transmission resonance